Welcome to KK Chemistry. Today we are going to discuss lecture number 16 and it is about derivation of term symbol for excited states, that is P3 system. You know that we denote actually the subshell by a small l and the term, you can say, spectroscopic term by a capital L and a capital alphabet as well. So here we take an example of nitrogen because it is a P3 system. You know that there are three degenerate orbitals and a p subshell. Okay, and this is denoted by like P, and the azimuthal quantum number is 1 for this particular subshell. And you know that if L is equal to 1, the subshell will be P. Okay, the rotation of orbital, you know that when this subshell is placed under magnetic field, it is, you can say, oriented into ml plus 1, 0 and minus 1. Okay, the 3 electron can be added in these 3D degenerate orbital in different fashion. Okay, how you will know that how many, you can say, energy levels are available to place these 3 electrons? You can calculate it by the formula of a microstate. We have discussed it earlier. You can go for the previous lectures. Here, the total number of, you can say, possible ways to place these 3 electrons are 20. So there are 20 possible ways of arranging these electrons differently. Just first place these 3 electrons n plus L, 0 and minus 1. Now, the ml value will be equal to ml1 plus ml2 plus ml3. ml1 is plus 1, so plus 1, 0 and minus 1, it will give us ml0. Okay, sorry for the slight pause. Now just invert this one. Okay, this is another arrangement. Keep on moving this electron in downward direction and this one in upward direction. Then you get another arrangement and so on. Okay, here the ms value is 3 by 2. How? Because plus 1 and plus 1, it will give us a 3 by 2. Now by calculating the spin multiplicity, it will give us a quartet state of the system over here. How? You can see it over here, 2s plus 1, by putting the ms value or the s value, it will give us a quartet. What means 4? So the spin multiplicity is 4 over here. That is why we have written it as quartet over here. For this very system, you know that the ml value is plus 1 plus 1 plus 1, 0 and minus 1, 0. Now the s value will be equal to 1 over half plus 1 over half minus 1 over half. It will give us S value or MS value is 1 by 2. Now calculate its spin multiplicity. You know that MS or S is equal to 1 by 2. Putting these values in the spin multiplicity formula, the resultant answer will be a doublet, means 2. So the spin multiplicity in this case, the spin multiplicity in this case will be from here up to here, it will be doublet. Okay, the rest are not because we don't have any spin multiplicity with negative or zero value. Okay, so this one is not applicable, but here we have just shown the maximum ways of arranging these electrons. Keep in mind, when you calculate the ml value, this plus 1 just show the orbital orientation, and this one show the number of electron in that particular orbital. Okay, remember that spin multiplicity cannot be 0 or negative. Now move forward. Here it is the partial pigeonhole diagram. In the first case it was a complete pigeonhole diagram for P3 system. Okay, again we have just paste it over here by removing the S value with minus 1 by 2 and minus 3 by 2. The same type of arrangement is over here. Here the MS value is 3 by 2. Spin multiplicity will be quartet. Here the MS value is 1 by 2. So it's 2s plus 1. The spin multiplicity will be doublet. Okay, the ml value you can just calculate is plus 1, 0, minus 1, 0. You can calculate the rest of these ml values. Okay, now how many sets we have over here? Okay, we can calculate the maximum number of term symbol from this particular, say, system or pigeonhole diagram. How? Set 1, this one. Okay, where the ml value is 0. So you know that when ml value is 0, the term will be S. And again, as you know, that this 0 lies where? In a quartet state over here. So the spin multiplicity will be quartet. Okay, the spin multiplicity will be quartet. It is S is 3 by 2. Okay, so the term symbol will be quartet S. Another set where the ml value is 1, maximum 1 mean plus 1, the small level plus 1, 0, minus 1. The term will be P in case when the ml value is 1, like this. So S plus 1, 0, minus 1 lies in the doublet state, where S is 1 by 2 over here. So the spin multiplicity will be doublet. The term will be doublet P. Set 3. Third one set. Here the maximum ml value is 2, means we have small ml plus 2 plus 1, 0, minus 1 and minus 2. This is small ml values. So when n is equal to 2, the term is a D. As you know that lies or you can say exist in the doublet region. So the spin multiplicity will be 2 and the term will be doublet D. Now which one is the ground state? According to Hund rules, if you have number of term symbols, then the term symbol with the highest spin multiplicity will be the ground state. So this one is the ground state. Okay, total degeneracy. Now how can we find the number of possible ways? It can be just find out by calculating the total degeneracy, mean 2l plus 1 orbital degeneracy and 2s plus 1 spin multiplicity. Here if l is equal to 2 mean d, it is you can say a subshell d with spectroscopic term capital D. Okay, so l is equal to 2 and we know that the spin multiplicity is 2. Just by putting these values in this equation, it will give us a 10. The second one, when l is equal to 1, just put the value of l over here and the spin multiplicity 2 over here, it will give us 6. And for s we have a 4. The total degeneracy will be equal to 20. We have just verified it because we have calculated the number of microstates earlier in our previous slides. Thank you very much. I'll be pleased to answer if you have any question. Please like, share and subscribe my channel for more useful videos. Thank you.